Podría haber sido un meteorito, un tsunami. Podrían haber vuelto los dinosaurios o llegado los marcianos. Podría haber sido una bala, una bomba o una guerra, pero fue una pandemia. Encerrados desde nuestra ventana, miramos un mundo paralizado. Quedamos desconcertados, atónitos, tratando de imaginar cómo seguir mientras se desmorona lo que habíamos creado. ¿Qué será del futuro? ¿Qué hacemos con lo que sabíamos y ya no sirve? ¿Cómo desaprendemos lo antiguo para abrir paso a lo nuevo? El destino se nubló y hoy navegamos a la deriva tratando de leer las señales entre la niebla. ¿Podemos entender lo que no conocemos? Hoy sabemos que somos pequeños, que nada es absoluto, estable, permanente. Necesitamos reconstruirlo todo. Relaciones, estructuras, códigos, nuevos sentidos para vivir en la fragilidad, nuevos acuerdos para atrevernos a ser diferentes, nuevos equilibrios para recorrer otros caminos. Recuperar lo humano como la más moderna de nuestras tecnologías. Hoy, por fin, y aunque nos asuste este salto al vacío, nos podemos reinventar. Congreso Futuro. Habitar la incertidumbre.
Now we are ready. Good afternoon, everyone. Welcome to the Congreso Futuro 2021, Antofagasta region. The Universidad Católica del Norte is glad to host this event. We want to welcome our distinguished invited speaker, one of the winners of the Nobel Prize in Physics of 2020, Professor Reinhard Genzel. And we will give more details about his CV a little bit later. We also want to welcome the president of the Comisión Desafíos de Futuro, Senador Guido Girardi, the rector of our Universidad Católica del Norte, Mr. Jorge Tavilo, authorities, researchers, and the public who is now with us today in this streaming. This is an unprecedented global context now. We are with the COVID pandemic, and we will discuss what we have done and what the challenges are for the future of science and astronomy. So to begin this activity, the Senator and President of the Comisión Desafíos del Futuro, Mr. Guido Girardi, will say a few words.
Quiero enviar un saludo al Congreso del Futuro que se está desarrollando en la región de Antofagasta, particularmente a la Universidad Católica del Norte, que ha, entre otros, llevado adelante esta tarea de difundir y democratizar el futuro. El Congreso Futuro lo acabamos de inaugurar ahora en Santiago. Van a participar cerca de 80 de los principales intelectuales, filósofas, científicas del planeta. Es una oportunidad gigantesca, es un verdadero privilegio para Chile de transformarse en uno de los principales centros de pensamiento nuevo a nivel mundial. Este Congreso Futuro, primero, es uno de los más importantes en Latinoamérica, pero también uno de los más importantes a nivel mundial, y es uno de los pocos que además es gratuito y es un espacio de intersección maravilloso entre las universidades chilenas, entre la ciencia chilena, pero también junto con el mundo político, de decisores, de gobiernos y de las regiones. Es un cruce absolutamente, yo diría, sinérgico para el siglo XXI, pero que además tiene otra característica: es una intersección con el mundo y la comunidad científica mundial, que es una oportunidad gigantesca para Chile, y particularmente para el norte, particularmente para el ecosistema del desierto de Atacama. Yo creo que Chile tiene oportunidades gigantescas, pero miren la casualidad, la mayoría de estas oportunidades gigantescas va a pasar por la región de Atacama. La crisis planetaria, el cambio climático nos amenaza como especie, nos amenaza como humanidad, a todos los seres vivos. Tenemos que pasar una era poscarbónica. Para eso tiene que haber una alternativa, que tiene que ser energía limpia y renovable para todo el planeta. No es fácil. Y Chile tiene la oportunidad de darle energía solar o energía eólica transformada en hidrógeno a todo el planeta. Trajimos a Carlos Rubia a la región de Atacama. ¿Y Carlos Rubia qué decía a la región de Antofagasta? ¿Qué decía Carlos Rubia? Que un pedazo del desierto de Atacama le podía dar energía a todo el planeta. Y eso se ha materializado, se está concretando. Por lo tanto, no solamente hay un inmenso, por así decirlo, una inmensa oportunidad para la región de Atacama, para generar empleo, para generar expertos, doctores, técnicos, sino la región de Antofagasta puede ayudar a salvar a la humanidad, y creo que hay una dimensión altruista. O, por ejemplo, podemos instalar los data centers más importantes. Las nubes a futuro son un negocio gigantesco de guardar, almacenar datos, pero requieren de cantidades energéticas también gigantescas que lo hacen absolutamente vulnerable y requieren de espacios geopolíticos seguros. Bueno, eso es el desierto de Atacama. Podemos ser un centro mundial de data center. Vamos a ser ya la principal ventana para explorar el universo. Desde Chile se van a descubrir los planetas habitables, pero estamos trabajando con la NASA para que no solamente seamos la ventana del universo, sino seamos el puerto del universo para instalar las futuras naves que van a ser impulsadas por rayos láser, que se tienen que instalar idealmente en el desierto de Atacama, para que puedan abordar justamente la exploración del universo, porque podrían alcanzar velocidades que solo esas naves impulsadas por rayos láser pueden hacer para hacer viable la exploración del universo. Y por lo tanto tenemos oportunidades también de usar nuestro mar, que ahí tiene la corriente de Humboldt, que lo hace uno de los mares más productivos del planeta para la acuicultura, y podríamos alimentar de manera saludable una parte importante no de Chile, de toda la humanidad, con los mares chilenos y los mares que están frente a la región de Antofagasta. O podemos ser uno de los centros mundiales del turismo que yo llamo turismo espiritual, que es uno de los turismos más maravillosos que tiene esta región. Entonces, creo que estamos llenos de oportunidades, y para eso necesitamos ciencia, necesitamos colaboración, necesitamos audacia, necesitamos creatividad, pero eso se tiene que hacer de abajo hacia arriba, no desde el centralismo, sino justamente desde la colaboración, desde que la comunidad de la región, sus universidades, sus científicos y científicas, sus decisores, sus empresarios, sus organizaciones sociales, su pueblo originario decidan de común acuerdo cuáles son las vocaciones de uso de ese territorio, que establezcan un consenso dónde se van a desarrollar estas actividades, y tengamos esa región como tal vez el barco insignia que va a mover el desarrollo de Chile. ¿Y por qué no decirlo? Tenemos que pasar de la minería, una minería totalmente tradicional, a que gracias al hidrógeno, gracias a la energía renovable, ya una mirada de futuro, podamos tener la minería verde más potente del planeta para nuestro cobre, pero también para el acero. Y esa región tiene todas las condiciones de ser de verdad el barco insignia que lidere. Quiero enviar un saludo al Congreso del Futuro que se está desarrollando.
It was like a journey, and super excited. And the result, of course, is wonderful. Okay, we appreciate the words of the Senator Girardi. Now, the rector of the Universidad Católica del Norte, Mr. Jorge Tavilo, will give a few words. El rector de la Universidad Católica del Norte a continuación nos dará unas palabras de bienvenida a nuestro invitado.
A little bit, a few words.
A few words.
So you are very welcome, Professor Jensel, Professor Onaka, and Professor Garcia, also Professor Maximiliano Moyano. I'm going to speak in Spanish because I have not prepared an English speech. Bueno, nuestras universidades regionales, particularmente nuestra Universidad Católica del Norte, está desarrollando un quehacer que está muy conectado con nuestra realidad que tiene que ver con habitar el desierto. Habitar el desierto significa doblegar el desierto, significa que nos enfrentamos a una serie de barreras como los temas de las problemáticas de recursos hídricos, los efectos laterales de lo que tiene que ver con la explotación minera, el desarrollo, ¿no es cierto?, de nuestras economías que están atrapadas en lo que se llama la trampa del ingreso medio. Por lo tanto, nuestro interés fundamentalmente es poder desarrollar economías a las cuales le apliquemos valor agregado. Nuestra institución tiene características muy especiales porque está ubicada en el norte, es para el norte y todo eso que hacer tiene que ver con nuestra realidad, sistemas geológicos, ciencias del mar, ¿no es cierto?, antropología, arqueología, astronomía y por supuesto todo lo que tiene que ver con las ingenierías de procesos son nuestra fortaleza. Pero yo creo que una de las cuestiones importantes de destacar es que estamos difundiendo conocimiento descentralizado. Creo que ese es el gran avance que ha tenido este Congreso del Futuro. Una cuestión fundamental es poder transmitir ciencia a la comunidad para poder entusiasmar a los jóvenes. Los jóvenes cada vez les cuesta más estudiar la ciencia dura. Algo pasa en el sistema que parece ser que buscan las cosas fáciles, por lo tanto este tipo de eventos, su objetivo principal es motivar a la juventud, educar también a nuestra sociedad y de esta manera ir formando, ¿no es cierto?, y motivando a la juventud para poder estudiar ciencia. La ciencia, digamos, tiene dos elementos, uno es lo que es la ciencia fundamental, que nos enseña, nos desarrolla el espíritu crítico y por supuesto también las aplicaciones. La importancia, ¿no es cierto?, es ser capaz de desarrollar una cultura en nuestra sociedad de tal manera de que también la ciencia se aproveche para lo que tiene que ver con la gestión, yo diría, de nuestras autoridades, que cuando se tomen decisiones, estas decisiones estén basadas, ¿no es cierto?, en datos científicos, en datos analíticos y no se tomen de manera, yo diría, intuitiva, ¿no? Y por eso que esto también tiene como fundamento poder transmitir estos conocimientos a nuestra sociedad. La verdad las cosas es que estamos muy orgullosos de que como institución estemos desarrollando tanto en Coquimbo como acá en Antofagasta este congreso. También hemos realizado una serie de otros webinars, ¿no es cierto?, que tienen que ver con la difusión de la ciencia a nuestra sociedad. Por tanto, yo quisiera felicitar a todos los expositores de hoy, especialmente al doctor Moyano por su entusiasmo, digamos, que tiene para poder muchas veces trabajar en estos temas que a veces como que no son muy valorados por los científicos, pero sin embargo los impactos que tienen, digamos, no son menores en el desarrollo también de nuestra institución. Así que bueno, darle la bienvenida a toda la comunidad virtual que de manera muy atenta van a seguir este evento. Así que bueno, solamente eso y muchas gracias por estar el día de hoy participando en este webinar, en este conversatorio. Eso es todo, Maximiliano. Muchas gracias. Muchas gracias por estar con nosotros.
Muchísimas gracias por su palabra, rector. We appreciate the speech of the rector of our university, Mr. Jorge Tavilo, and now we have to excuse him because he has to disconnect now from the webinar.
Okay.
So now,
okay. Bye.
Bye. Okay. So today we have the honor to share this event with the Nobel laureate in Physics 2020, Dr. Reinhard Genzel. He will tell us about the wonderful science that led to the confirmation of the supermassive objects at the center of our galaxy. Professor Genzel earned his PhD in physics and astronomy in 1978 from the University of Bonn in Germany. Immediately after that, he was a postdoctoral fellow at the Harvard Smithsonian Center for Astrophysics in Cambridge, Massachusetts, in the United States. And many other recognitions, but then currently now he is the director of the Max Planck Institute for Extraterrestrial Physics in Garching, Germany since 1986, and a full professor at the University of California, Berkeley, USA since 1999. Reinhard Genzel was awarded the Nobel Prize in Physics 2020 together with Roger Penrose and Andrea Goetz. The Royal Swedish Academy gave the prize to Professor Genzel for the discovery of a supermassive compact object at the center of our galaxy. Part of his work has been possible thanks to the European Southern Observatory facilities located in the region of Antofagasta, Chile. So that's why we are super excited to hear his talk now, because it's really connected to our north of Chile. So on this occasion, Dr. Reinhard Genzel will talk about the amazing story behind the study of the compact object in the galactic center, titled A 40-Year Journey. Professor Genzel, thanks again for being with us today. So now the streaming is yours, please. Thank you again.
Well, thank you very much, dear colleagues, ladies and gentlemen. Yes, I would like to tell you about a fairly remarkable journey we've taken over more than 40 years, in fact, in my case, to use big telescopes and new techniques to check out the proposal of general relativity, as you will see, that there are objects in the universe where light can't even escape, and where all the mass of these objects is supposed to be at the very centers in a very dense, infinitely dense central mass singularity. These objects called black holes, of course, have become lately part of our culture because of movies and science fiction and so forth. But the story I will tell you about is really one of hardcore scientific experimental work. And as Dr. Mariana already said, much of this work has been done initially in La Silla, and then most of the recent work and the culmination of the last 15 years on Paranal Mountain with the telescopes of the European Southern Observatory. So the story which I will tell you is really 100 years old. It is the story which emerged after Albert Einstein had published in late 1915 his theory of general relativity, which was basically a way to describe Newton's results in a still better and more profound way. And what Einstein basically said is that the gravitational interaction, which of course we as human beings know when we stand on the surface of the Earth and try to jump up and we fall down immediately because the gravity pulls us back, that interaction, that gravitational interaction, you should think of as distortions in the so-called space-time. So think of basically our space in which we live, which has 3 dimensions, and the time which passes as sort of a 4-dimensional construct. And so if you have a mass, which in this picture would be 3 masses, a very heavy mass, which is the green-yellow object, and a brown, not so massive object, and then a much less massive object, which is the red one, then they basically dent space-time. And so then what Newton would describe as the interaction through gravitational forces in Einstein's theory basically is considered to be a path of an object through space-time, and the interaction, the attraction, which a planet would feel moving around the sun would be due to this dent in the space-time, which then deviates the orbit from a straight line into a curved orbit. So that's the idea in Einstein's theory. Now, as I will explain a little more in detail, this means that, in fact, also light itself is affected by these masses and gravity. Light we would think of as waves in classical physics, but it's the communication speed, of course, which is maximum. Nothing can go faster than the speed of light. And if light rays go through space-time, they also will see these dents and will be affected by them. Now, the theory of Einstein is a very complicated mathematical construct. But indeed, already 1 year later in 1916, Karl Schwarzschild published one solution for the simple, most spherically symmetric solution of a mass, which was, so to speak, by itself, and showed that, in fact, these features like, the space-time perturbations, but also that light would be affected by the masses, was contained in it. Then it took another 50 years until more solutions, mathematical solutions, could be found. And in fact, Roger Penrose, the one who got the Nobel Prize with me last year, was the one to show that these objects, which we now call black holes, are not just mathematical constructs, but that they are likely going to be actually realized in the universe. And this realization that there are such objects in the universe came about starting in around 1963. Then radio astronomers discovered radio stars, objects which they saw in radio waves. But then when the optical astronomers looked at the same objects, they would see faint stellar-like objects, like in this case, the Cambridge radio star 3C273 looks like an ordinary unresolved star. But when Martin Schmidt, whom we see down there, used the Palomar telescope to look at the spectrum, so the colors of this radio star, what he saw was very distinct features we call spectral lines in the optical spectrum, but all redshifted by 16% relative to our laboratory rest frame. How can you have this redshift? Well, at that time, astronomers already knew that the universe was expanding. So one could interpret this redshift as a result of the cosmic expansion. And then this little star there is actually 2.5 billion light years away. So that's a significant fraction of the age of the universe. So we're looking back in time, basically, looking at an object as it was 2.4 billion years ago. And so what then looks like this faint little stellar-like object actually, in reality, must be very, very luminous, 1,000 times more luminous than the entire Milky Way. And obviously all in a very compact configuration, because otherwise you would not see it as a star. So that was the discovery of what we call quasars, quasi-stellar radio sources. So astronomers immediately started thinking about, well, how could you possibly power such extremely luminous yet compact sources? It became clear that fusion, so the fusion from hydrogen into helium, which powers stellar objects like our sun, were not sufficient in quality to do this. But actually, if you let material fall onto a black hole, paradoxically, you can. So a number of theorists worked that out over the next decade into the early 70s. So the idea is you have a black hole in the center, and gas, which falls into the center region attracted by the mass from the black hole, falls in. But typically there is some amount of what we call angular momentum. And so like in the planetary system, the solar system, this infalling gas then takes on the shape of a plane, a disk, and slowly by friction moves inward. And as it moves ever closer to the region which even light cannot escape from, so this innermost region around the black hole, the hotter it gets. And before it disappears from our visible world, so to speak, it really is very luminous and can explain, at least theoretically, these quasars. So by the early 70s then, as ever more quasars were discovered ever further away, the paradigm which most everyone had developed was that this was due to accretion of gas and stars onto massive black holes. How massive? Well, between millions to billions of solar masses. Incredible objects which obviously nobody had previously thought about. Well, that's a hypothesis. How could you possibly prove it? Well, by measuring, in fact, gravity itself. How do you do that? Well, let's do a little thought experiment. And here we have our Earth. And you all know that we can shoot a rocket into space away from the Earth. In order to get a rocket outside of the Earth's atmosphere into space, we have to accelerate the rocket to about 40,000 kilometers per hour, which is 11 kilometers per second. So for an object like the Earth mass and a 6,000 kilometer radius, gravity is, moderately large, and a rocket has to have that speed. Now let's, in our thought experiment now, make the Earth ever smaller. Gravity is proportional to the mass and inversely proportional to the size. So as you make the Earth, our hypothetical Earth, ever smaller, the stronger becomes gravity. If you make it 1 centimeter in size, 1 centimeter instead of 6,000 kilometers, then you can calculate that now the escape speed of our rocket is 300,000 kilometers per second. Not 11, but 300,000 kilometers per second. Well, that's the speed of light. So that means that an Earth of 1 centimeter in size could not send out light because light would not be able to escape. So that's one feature of what we would call a black hole, because there's obviously a radius, which in this case is 1 centimeter for the Earth mass, within which light cannot escape anymore. And now you can create, if you like, in your mind, such black holes of any size and mass, if you like. We don't know whether they are realized in nature, but that's the general idea. So to speak, in that case, that object disappears from our sight. Light cannot escape. It's black. That's the black hole. So how do we prove that there is a black hole there if you can't see that there is one? Is there a way to do this? And the answer is yes, by the action of this black hole onto the space-time around it. If there are other objects in this space-time, they will also sense this Earth. It's just like in the solar system. If you have the sun in the center, the planets are orbiting the sun like in circular orbits almost, and the more distant planets move slower than the further in planets. And these are Kepler's laws or Newton. And so in general relativity, the same is true. If you think now of a solar system around our hypothetical black hole Earth, well, then the inner orbits, the Mercury, Venus, would move, and they would move faster, and the outer ones slower. So now you can see how one possibly could test the idea of whether, there is a massive black hole somewhere by using objects like stars or gas, planets, surrounding this object and measuring its motion, and see whether, these typical patterns of the Keplerian motion would be there. Now, it's not that simple. In the case of the center of our own Milky Way, which is the closest galaxy, it's much, much closer than the nearest quasars. The first problem we are sitting in the outer parts of the Milky Way. So if we suppose that a massive black hole would be in the inner parts, the first thing is we have to see into the inner parts, and these dark patches in the optical pictures is dust between the stars, interstellar dust, which attenuates the light greatly. So we actually cannot observe the galactic center in visible light. We have to go to wavelength where we are not inhibited by these dust particles. And that you can do in the radio, you can do it in X-rays, you can also do it in the infrared, which is only a few times the wavelength of light. So if you do this in the galactic center, then you see that there's an incredibly dense star cluster, 1 million times denser than our environment here around the sun. So at night in the galactic center, it would be incredibly light outside. And you don't only see stars there, you also see gas, which you here have in green and also in pink color. This is neutral gas, an ionized gas, which happens to be in the center. And with new instruments which were becoming available in the infrared and millimeter range, astronomers starting looking at this innermost region exactly to test the hypothesis whether there might be a central heavy object here. In fact, it was another Nobel laureate, Charlie Towns, who got his prize for the invention of the maser and the laser, who in his later years started to do astronomy. He and his students, and I then became a postdoc in his group, we started measuring the motions of these ionized and neutral gas clouds, this green and pink stuff there. And what we could deduce from this is that, and you see this in the lower right, if you plot mass on the vertical axis and the distance from the center on the horizontal axis, you note this is in logarithmic units, so every tick there is a factor of 10. Then, if you go to very large scales, then the mass increases as you go away from the center. That is extended mass in the star cluster. But then within about a few light years, the mass remains at about a few million solar masses. So that was in the 1980s, the first evidence we have from these gas motions, that there was an unusual amount of mass in the central region, so large that you could not explain that easily, even with the stars. So although the star cluster, as I explained to you, these blue things, it's very dense, there was not enough stars there to explain this. Then the radio astronomers looked at the center of all of this, where you see this red, white little circle, and looked at it in the radio and found a very compact radio source, which we now call Sagittarius A star. On the left diagram, what you see is the size, the angular size of that radio source as a function of wavelength. So at very long radio wavelength, you see the size is still reasonably large, but then the shorter wavelength you go to, the smaller it becomes. And in fact, in the shortest millimeter wavelength where we can do this measurement, the size is about 40 micro arc seconds. That's about 1,000 times better than what we can see with our own eyes. And it corresponds to about a euro cent coin on the moon. So it's an extremely compact object, and just about as large as you would expect from an object of about a few million solar masses if it were a black hole. So this idea, this proposal that there might be a compact mass, a black hole in the center of galaxies, became a possibility in the mid-80s. But is that a proof? Well, no, because there's still other possibilities what you could have. You could have a concentration of stars which are not very bright. You could also have rocks, if you like. If you squeeze them into this central region, you might, see the same kind of mass. So in order to prove really without any doubt, you have to go very much closer. And you also have to have better tracers than gas. Gas is not the perfect tracer of gravity. So what we need is better resolution. We have to look at stars, and we have to make very precise measurements of the stellar motions. So when we started all of this in the 90s with the stars, there was a lot of technology to be done, because we knew we had to measure in the infrared, and the detectors at that time in the infrared were pretty bad, so we had to have better detectors. The next thing is, when you look in the infrared or in the optical, from Earth outside, then it's like on a hot desert day, and you look at the distance car which is coming at you, the images of the car are starting to flimmer, and that's what we call seeing. So we have to overcome the seeing, and nowadays we overcome that by correcting the light by so-called adaptive optics. I show you how that is done. And then, many more technologies had to be developed in order to do this kind of measurement. So let me tell you about the adaptive optics. So the waves from a distant star, as it comes into the atmosphere, get distorted. You see these little wrinkles in the waves. So when you then, focus your light onto a detector, your distant galaxy or star becomes fuzzy. However, if you put a so-called deformable mirror and you measure the distortions and you deform the mirror in order to straighten out the wavefront, then all of a sudden the images become sharp again. So that's what we call adaptive optics, and that's a technique which was developed in the 1980s and is now standard. In fact, most nights we use it on Paranal Mountain, and in fact the next generation telescope on Amazonas near Paranal will only work with adaptive optics. Another technique which you have to develop, and we had to develop, is so-called integral field spectroscopy. Because you want to have spectra over a field, over an image, you have to image and do spectra at the same time. That's not so easy, actually. So that was a technological breakthrough which had to be done. And then finally, to make these corrections with adaptive optics, you need a bright star very close to the object. In the galactic center, actually, there are such stars, but typically they are not. So what do? Well, you make your own star. So what we do nowadays, we send laser light and focus it in the upper atmosphere. Here you see at this in wavelength of sodium, this yellow beam, basically making sort of like a streak of light. You focus it in the upper atmosphere, where it's reflected by sodium atoms at 90 kilometers altitude, and then reflected back to the telescope, where we can then analyze the light waves and use adaptive optics. So you can see that this kind of research we're doing has a lot to do with pushing the kind of technology you require in astronomy to the new heights. And we've done this in several phases over these last 40 years, and I'm just summarizing for you the kind of things we had to do. Another thing is you have to have big telescopes. When we started, we had a 3.5 meter telescope in La Silla, but then fortunately, a few years later, the Paranal Mountain with its 8 meter class telescopes, and also on Mauna Kea, the 10 meter class telescopes, came into operation. So we want to have the biggest machines we can have in ground-based astronomy. Now I'm talking about work now, which over the next years happened both in Chile, that was our group, on the ESO NTT and the VLT, and then also on the Keck telescope by a second group Andrea Guest's group, who shared the Nobel Prize with me, using the Keck 10-meter telescopes. And the remarkable thing is, having two groups compete is actually something good, because all science requires that if somebody says, "I found something," then somebody else has to confirm it. Otherwise, it's not considered be right. It's like fake news. So if you want to have truth, you have to have confirmation. And so the two groups basically conducted independently this research over the next 20 years and more or less agreed on almost every finding. So we now can, with adaptive optics, have much sharper images of the central region in the Milky Way, as you see this star cluster in the center and look at the motions of the stars. Initially, we just looked at the so-called proper motions. So basically, we took pictures, and then took another picture another year, another picture another year, and basically over time we looked for the changes in the images. And here you can see within a circle in green of about 1 light month, so very much in the very center around Sergei star, which is that green cross, pictures over 3 years in red, in green, and in blue in 3 consecutive years. And you can see immediately there's one star there next to Sergei star, which very obviously changes position. You also see, if you look closely, there are other stars which also move, but as you go away from the green point to the outside, the colors become weaker and weaker. That is an encoding of the Kepler's laws, in that the motions become smaller as you go further away. So that tells you qualitatively, immediately, that the mass which you have here, which causes that motion, is a concentrated mass. So how concentrated? Well, so if you make measurements of the motions as a function of distance from away from Sergei star, initially the motions are constant on the outside, that's the star cluster, then become faster and faster as you go further in. That's the Kepler's laws, as I just explained. And when you look at the amplitude of those motions, you can immediately deduce that there must be an invisible mass of several million solar masses, several million. At the time, we thought maybe 2 to 3, 2 to 4 million solar masses. So that really does look like what you would expect from a black hole. Of course, again, after we had the first result with stars in around 96, 97, 98, and the two groups agreed, you have to ask the question, are we done? Have we now proven that there's a black hole there? No, you have proven that there's a massive object there, and it's pretty concentrated, certainly within a light month. But must it be a black hole? Well, no, there are some alternatives. And so, unfortunately, science pushes you to the next step. You have to still do better. What could you do better? Well, instead of measuring the average motions of the stars over time, you hope to see orbits, so that individual stars, basically, as they orbit, tell you very precisely how much mass there is within the orbit. And so that was the big next step. And indeed, both groups in the next 10 years began to see these motions. And here, these are real data, of course, over many years, but still you see that the stars are moving. You can also see they're moving sort of in circles, some of them at least. So that's an orbit. So if you actually analyze these motions, you see that these are nice ellipses and circles of various shapes. And there's one particular star, which you see here, which is very highly elliptical, moves at its largest distance by a few hundred kilometers per second. But then in 2002, for the first time, approached Sergei star, and there moved with 8,000 kilometers per second. 8,000 kilometers per second. That's about 300 times as fast as the Earth around the sun. And at that point, when it was closest, it was on the scale of the solar system, about 3 times the orbital radius of the Neptune planet. And so if you combine this, an 8,000 kilometer per second velocity at around, 3 times the Neptune orbit, you can calculate the mass, and that comes out to be, again, 4 million solar masses. The same 4 million solar masses we had measured before. But now, within not light months or light years, but 17 light hours. So you have to squeeze 4 million solar masses into this small volume. So by the time this result was pretty solid in the mid-2000s, and both groups agreed, many people felt, oh, wow, I mean, that's really a pretty convincing piece of evidence for a black hole. So I show you this again here in terms of a graph where on the left side you see the mass as a function of time, which we estimated, as well as the accuracy of the mass. And so you see, slowly the measurements get better. Mass also changed some because we had different analysis methods. But, over the last 10 years, we were pretty convinced we had around 4 million solar masses. And the accuracy by 2017 was below 1%. So that was near 1%. And all of this had to be within now about 100 times the event horizon size of a black hole. So that's very, very close. So qualitatively, there's little plausible else than as a solution than a black hole. So by exclusion, we had excluded all these possible other configurations, and it might be indeed a black hole. So we asked ourselves, well, is it a black hole? Must it be a black hole? Well, the answer is, well, maybe. Plus, the proof here rests on general relativity. We assume that general relativity must be true. But you could come on and would say, how do you know this? Nobody has tested general relativity in this extreme range. So we saw that coming in 2005 and said, well, the star has an orbital period of 16 years. So it has to be coming back in 2018. So when it comes back in 2018 for its next Perry encounter with Sagittarius star, we must be ready to measure still better, still more precisely. So what did we do? Well, now we used a technique and developed a technique which the radio astronomers know very well, but the optical astronomers don't really know how to deal with, and that's called interferometry. So on the Paranal Mountain, which you see here, we have these four 8-meter telescopes inside of their domes, and we've been using the right one for the measurements I've shown you. But in fact, wisely, the fathers of the VLT had already seen the possibility that one could combine the light of the 4 telescopes to turn that into a 100-meter telescope. How does that work? Well, if you think of a light wave hitting 2 telescopes which are far apart, then you can take the light and instead of detecting it, you bring it together underground in a tunnel and interfere it there in a central station. Thereby, you construct basically a virtual telescope of the size of the distance between the telescopes. So instead of an 8-meter telescope, all of a sudden you have a 130-meter telescope and 20 times better resolution. So we were working on that. This is an extremely challenging experiment because the wavelength of light is so short and you have to measure this all on nanometer precision. There's earthquakes, as we all know, in Chile from time to time, seismic activity, et cetera, et cetera. So this is really challenging from a measurement point of view. But we did make it, and we were ready for the next stage of this experiment when the star came back with this machine we call gravity, which is actually located in the middle of these 4 telescopes underground where the light is combined. And we can measure with this to an accuracy of, about this euro cent coin on the moon. And when the star came back in 2018 and approached again to 17 light hours, we could see its motion, not from month to month or year to year as before, but from night to night. From night to night, we could see the motion, and you see this in these individual measurements. So we had a 20, 30 times better precision of our astronomical measurements. And indeed, with that, we were able to see effects of general relativity. One effect we saw is that general relativity predicts that as you have light coming at us from near a mass, then the clocks are going slowly near that mass, and the light is redshifted. And so below you see the measurement where we see this redshift in the spectra. General relativity also predicts that in Newton's theory, stars or planets orbit the sun on closed ellipses or circles. Not so in general relativity. In general relativity, there's the effect of the precession, which is built into the theory. And indeed, last year, we saw that precision as a sort of a kink in the orbital structure of that star. And then finally, we were able to actually see gas motions right next to the event horizon, due to a very hot gas in the plasma around the black hole, moving at around a third of the speed of light. So with these experiments, and probably more to come in the future, you see we now have a very precise measurement of the mass of about 1/3%. And we measure the constant of the mass of 4 million solar masses, essentially to within 10 times the event horizon or 5 times the event horizon size. So there's really truly no believable possibility that there's anything but a black hole. So let's ask our question again, are we done? Well, I'm a pretty old man now, but I'm eager that we continue. And in fact, as soon as we can come back and start our measurements again, we will improve gravity even further, because what we want to do now is to push still further in order to see more effects of general relativity, and in fact, perhaps test general relativity in a regime where it has never been tested. And that's something which is very, very important for physics. Now, these kinds of experiments, as you see, take a lot. It takes, first of all, time and patience. You also have to have the resources to go on. You have to have a telescope, which is good. You have to have a site like Paranal Mountain, which is the best in the world. And you have to have a team of people, both in Germany, in Europe, and in Chile, who work together for 40 years to do all of this. So that's what I would say, the beauty of science. You make discoveries, and at the end, you can learn more about the universe. Thank you very much.
Wow, this was an amazing talk, Professor Gensel. So we really appreciate this talk. Now, in the meantime, we invite everyone to send us your question on the chat box of the different platforms, and we will answer them. Professor Gensel will answer them at the end of the discussion. And now I would like to, Professor, introduce you to my colleagues that want to discuss with you your great results. Dr. Pablo Garcia here got his PhD in 2015 at the Physical Ages Institute of the University of Cologne, Germany. He was then a postdoc at the Institute of Radioastronomy Milimetrique IRAM in Granada, Spain, and he is currently a professor extraordinario at the Institute of Astronomy of the Universidad Católica del Norte, and also a researcher at the National Astronomical Observatories in China. His main research topics are the massive star formation processes and the interstellar medium feedback in the galactic center of the Milky Way. photon-dominated regions, millimeter and submillimeter instrumentation for astronomical research and atmospheric characterization. On the other hand, my colleague, Dr. Keiichi Onaka, got his PhD in 1997 at the University of Tokyo, Japan. He worked at the Max Planck Institute for Radio Astronomy in Bonn for 14 years before joining the Institute of Astronomy of the Universidad Católica del Norte. He's mainly working on the high angular resolution observations of evolved stars using the ESO Very Large Telescope Interferometer, as you were mentioning. For example, imaging the surface of stars other than the sun and mapping the motion of the their atmosphere and the formation of disks and jets around dying stars. My colleagues, for example, Paulo, I guess you have many questions, so I pass the now.
Okay, thanks, Max. Well, thanks again, Professor Gensel, for this really impressive and beautiful talk. I would like to bring you to another wavelength domain. As Max just explained, I come from a millimeter, sub-millimeter background. So, as you are well of, the EHT consortium has not published yet the results regarding the mapping of Sagittarius A star in millimeter wave. I have heard some rumors, not confirmed, that this is due to the fast continuing variability in the data on the order of days. So my question to you is, do you see any variability phenomena in the spectra of the stars that you map around Sagittarius A star in similar timescales, or any kind of variability that might coincide with what eventually people at AHT are detecting?
Absolutely, absolutely. In fact, that was from the beginning an issue we all were concerned about, which is that the time it takes for light rays going around the black hole on the innermost possible orbit for light is a mere 10 minutes, 15 minutes. And so that means, or 20 minutes, that means that if you have hot plasma there in the vicinity of the black hole, and that hot plasma, basically experiences accelerations and so forth, then the radio emission and the infrared emission and actually the X-ray emission all start to vary a lot. And we see that completely clearly in the galactic center. In fact, one of the effects we have seen is exactly these, what we call hotspots, which likely happen when magnetic field loaded plasma bangs into each other, accelerates electrons, makes infrared synchrotron emission, and that basically stays on and lights up for typically an hour or so, but varies a lot. And it's the same kind of physics which you would think could also happen in the radio. Now, what our colleagues with the Event Horizon telescopes want to do is another test of what I have tried to explain to you. So we're using objects with mass, stars and gas, and look at the motion, so to speak, at different radii and see whether that confirms. And sort of the next step further is you use the fastest thing you have, which is photons, and let it run around the black hole. And there is an innermost orbit for the photons, which is inside of our innermost orbits for the gas by some factor of 2. And so if you then can measure the size of this orbit, which shows up as a ring in the image, and you know the mass, and we know the mass, as I told you, to 1/3%. So we know the distance to the galactic center to 0.5%. We have a very precise prediction what the size of this ring should be like. So as soon as our colleagues are technically able to overcome the unfortunate effects of this flimmering of the hot plasma, which is a technical challenge. One can overcome it by basically taking many images and then sort of averaging over those, hoping that the variable part can be thrown away, so to speak. That's what they're trying to do. And you can extract out of this photon orbit. Then this is a very, very wonderful first-order test. And we know exactly within percent accuracy how large this ring should be. It better be the size which general relativity predicts, okay? So it's a super, fundamentally super precise way of testing with physics methods. The technical problem is that our colleagues only had 1 year in which they got good enough data, and that was in 2017. And that's when they published in the similar image in M87. But the mass in M87 is not very well known, and so you don't have a prediction like in the galactic center. Unfortunately, in 2018 and 19, they didn't get any data. So we very, very much hope that this year, our Event Horizon Telescope colleagues will get galactic center data, and then they manage to overcome the variability. And then, this is a beautiful test of general relativity. Absolutely.
Wow. Thank you, Professor Keiichi. I guess you have also questions for Professor.
Thank you very much for the very impressive presentation about your 40-year journey, Professor Genzel, and so this star S2 makes an orbit again. I just wondered if there is another unfortunate star that comes too close to the supermassive black hole, and then maybe I wonder if we can witness it disintegrate while it passes too close.
Right. Well, actually, I should say that, we are eagerly looking for other stars inside the orbit of S2 for other reasons, because there's another very important effect of general relativity, which we have not yet seen. And that's the effect of the rotation of space-time due to the spin of the black hole. So the black hole undoubtedly will rotate. How much, we don't know. And so if it does, it drags the space-time around with it. And if you have a star which is close enough, as S2 is not close enough to see that effect, then you could see that. So we are eagerly trying to do that. And, we have seen now a faint star closer in, but it's probably more projected than inside. So that's one of our main goals for the next years. Now, your question has to be answered in the following way. In order to get into this innermost region, any star further out in the star cluster has to be, so to speak, perturbed in order to make it into the central region. And that happens relatively rarely. You can calculate this typically once every 40,000 years. You would perturb an average star in the outer cluster where we see them running around. And then indeed, as such a star would come in to about, at less than a tenth of the orbital radius of S2, then it would not be stable anymore, and then it would be disrupted. Now, we have seen gas clouds which look like the remnants of disrupted something. And it's quite possible that, so to speak, we've seen the remnants of such disrupted stars, but a disruption itself is a fairly rare opportunity, but very important, because that obviously, if you see an effect like this, then you're very, very close to the event horizon, and that's exactly where your constraints on general relativity will be closest. The most likely way to do this is with gravitational waves. So in the end, I believe we have to be very lucky that we see such a star. I mean, what is the probability that in a few years, if this happens every 40,000 years only once, but in other galaxies it happens, and so we are hoping that there will be a space mission from the European Space Agency, ESA, called. Well, anyhow, it will be a space mission, ESA, which will see how objects would come into a massive black hole. And so, if you have a stellar black hole, for instance, spiraling into a massive black hole, then you would see such effects.
Exciting times.
Thank you,
Paulo, you have more questions for Professor?
Yes. I would like to come back to the theoretical physics of the black hole. The Sagittarius A star has been, as you just showed, to test GR under very extreme environments, right? Like the precession of the S2 star, the gravitational redshift, and so on. But do you think that quantum mechanical phenomena, such as Hawking radiation, could be tested close to the Schwarzschild radius? Or do you see it feasible that at some point in the future, either supermassive black holes or smaller black holes can become kind of the laboratories where we can test theories that might unify?
Okay, so let's first explain to the audience what you're talking about. So basically, the idea is within this cloak, which I told you a black hole has around it, the event horizon. I told you nothing can get out of this. Well, actually, that's an answer which is only true in classical physics. In quantum mechanics, you can have an effect right at the event horizon, which is called tunneling, where because of the uncertainty principle of Heisenberg, a particle might be generated where the particle goes into the black hole and the antiparticle goes out of the black hole. And that's what you called Hawking radiation. Now, this process in its thermal limit, you can calculate how much radiation you would expect. And that's what Hawking has done. And unfortunately, I have to tell you, the temperature is so low that for current methodology, it's absolutely hopeless. However, that's not, there may be progress in scientific methodology and other ways that other effects of quantum effects might become possible. And one of those is has to do with the same thing, which is the loss of information. So for Einstein, for classical relativity, it doesn't matter how you generate the mass of a black hole. Yeah, you can throw in rocks, a few cars, a few astronauts, and so forth. The black hole will forget everything because all the mass, according to Einstein's theory, will be in an infinitely dense point in the center. That is unlikely to be true. The quantum corrections, which must be there at some level, would maintain quantum numbers. I mean, that's a very alien concept to most people, but to the quantum physicists, they are very convinced. It's absolutely impossible to destroy. Therefore, the black hole must know I had 10 cars, 3 astronauts, and a few planets and so forth, which I gobbled up in my life. And it can tell you the masses, et cetera, et cetera. So this information must be there. And so if we can get at that information in a way that's coupled to the Hawking radiation, sometime in the future, maybe if you live long enough, you might look at that problem.
I mean, after the achievement of measuring gravitational waves and all the technical implications that it took, who knows what's going to happen in 10 years.
Yeah, no, but it of course, look, it's extremely difficult. As I told you, under current, estimates, impossible. But that's the challenge of basic science. That's what makes science so incredibly exciting, to understand things and go to the limits of where nobody ever has been before.
Wow, really exciting times. Keiichi?
Yeah, I have another question, but in a little broader context. So what was the most difficult problem or the most challenging aspect of your 40-year enterprise or 40-year quest for the central object? I mean, not only scientifically or technically, but also in general, for example, big collaboration or forging a very strong team or support from the institutions or whatever it is.
Well, I would have to say, luckily, this experiment, as in retrospect now, complicated and long and all of this, it looked at any given time in earlier times, it was just one step after another, and so in that sense, the steps we took did not seem insurmountable or impossible until the interferometry started. I think it was clear that the interferometry was a very big step forward, okay, and extremely difficult. And it did turn out to be extremely difficult. I would say gravity, you might say, is probably, other than the gravitational wave experiments, one of the most difficult astronomical experiments which has ever been constructed. Okay, but there were other challenges. I mean, one challenge early on was detectors. We wanted to make these measurements, but we knew this was before adaptive optics, and we had to take short exposure images, what you call speckle images, to overcome the Earth atmosphere. Well, for that you have to have a detector which doesn't have much noise, and in Europe we didn't have such detectors. So the only ones who had them were the American military.
Yeah.
And so to get at those in the Cold War times was impossible.
Yeah.
But we were lucky that indeed Cold War ended, and Charlie Towns, whom I mentioned, was very close to all of this, and told the American military that they should declassify some of these technologies, and that would benefit the astronomers. So that's how the Hubble Space Telescope got this detector, and we were then able to get the detector over to Europe in time. So that's another challenge. Another challenge is, for young people to enter, the risk of having a scientific career. It's not a job which is guaranteed. You know this yourself. I mean, you have to take the risk. You have to go to different countries, and I applaud you that you've done this in your life, and it's great for your country now. I mean, I think what's happening in Chile in the scientific community is fantastic. I mean, it has so many new things which will benefit the country on the long run.
Thank you very much for your words, Professor. I have a question, so I want to use the time also to make a question. So, and related also to a broader context or what you were mentioning before, with the upcoming ELTE, Cherenkov Telescope Array, and other astronomical facilities that will come to Chile, to the north of Chile. Of course, largely improving the astronomical instrumentation capabilities we have now. What would you say are the main astronomical questions that we will be able to answer in the next decade with the new observations that will be actually taken from the north of Chile? So what is your...
Right. So, well, basically, let's take the ELT. So the ELT is going to be a 40-meter telescope, not a 39-meter telescope. So it has a resolution which is 5 times better than the VLT. So that's pretty impressive, although mind you, gravity has more angular resolution than the ELT, okay? So it's not the resolution by itself. It's the combination of resolution and this enormous collecting area of a 40-meter telescope, which is going to do the trick. And there, that means to me, and that's what we, in fact, if I stay healthy and still active to this time, that at the very end of my career, we are building this first light camera, and we want to look back in time. We want to see the first galaxies and the first star clusters at the highest redshifts. And the ELT is going to be just as sensitive as the JWST in the near infrared, but because it's so much higher resolution in angle, it can really very decisively see compact things like, for instance, the first globular clusters. And that would be a triumph to see the first star clusters which had formed after the Big Bang. That would be also one of the many things which you can think of. Exoplanets, of course, will also be a tremendous research area for these big telescopes, because again, the combination of the high angular resolution and the highest great sensitivity. Now, for you in Chile, I think, if you allow me to give you advice, it's important that you participate in this actively. And so I think, we've done that already now with the young Chilean researchers, brought them here to Europe as postdocs, and they've come back as professors, very much like you. And Chile has to build up a active scientific community which can take full part in this endeavor. Now, if you want to do that, however, you have to have the capabilities laboratory-wise and the resources money-wise to participate in machines which will cost 20, 30 million euros and will have numbers of a few hundred people. Now, not a single institution will do that. Okay, we don't do it either. But you have to have the capability to participate in these kinds of experiments at the level of 1 million or so. That would be very, very important.
Thank you very much, Professor. And now we will read some of the questions that the audience sent us, and that also they sent them before. One question that you already mentioned, that then it was written by the public. Jared asked, in the future, could gravitational waves be used to study black holes in the center of galaxies, or that only works for events like mergers?
No, absolutely. I mean, I would say, in fact, if I would save money on the ultimate experiment in this research area, it's LISA. The problem is, there is a very wise statement I've learned as a young researcher: only go to space if you must. Because, okay, I was lucky in my career in that during my period as an active researcher, we were PI or co-PI institute of 2 big space missions, okay? The ISO mission of ESA and the Herschel mission. And so, that was great. It was fantastic. But these missions typically happen only every 20 years. And there are many, many possibilities for delay. As you see with the JWST, I mean, the poor people who have been building the instruments for JWST are now waiting for 20 years. And that's a very awkward situation. So that's why the LISA community, whom I know very well, they told ESA and on NASA what they wanted to do and how they would do it already in 1990. So they are waiting now for 30 years, and they have to wait another 15, 20 years. So that means, just building the instrument, getting it going, takes more than a generation. And that's very frustrating. And so that's why, on the one hand, this is the ultimate experiment. On the other hand, if it takes too long, or in the case of particle physics, you're only 1 out of 4,000 people. That takes the fun out of it.
Yeah, for sure. It's a difficult part. And finally, the last question that was sent to us, a general question. What would you tell to a young student now that is thinking to become an astronomer, and what would you tell him to motivate him?
Yeah, well, I mean, quite obviously, if you look at the emerging or the fields of the future that we mentioned already, the two towering directions. One is cosmology at the very highest redshifts or the largest look-back times, including effects very close to the Big Bang itself. And the other one is exoplanets. There's no doubt that exoplanets is going to be a field of great discovery. Now, of course, the current time, which I might describe as the botanics of exploring the forest, will come to an end. You see what I mean? I mean, the phases in astronomy sometimes are you discover a new forest, and then you walk into the forest and you very carefully observe what there is. And you see the trees, of course, and then you see some flowers, and blue flowers and red flowers and green flowers. You all take a note of this. And that's the botanics part. That's good. It's highly exciting, but it really becomes exciting when you start getting into the second part, where you see that the blue flowers are always on the left side of the road, and the red flowers are always on the right side of the road. Wow. You then have to ask yourself, why is that? Because that's the road to understanding and not just exploring. Okay. And so there's finding 4,000 exoplanets is really exciting. But the next big questions undoubtedly will be, how did they form? How important were migrations? How did this all happen as a function of the mass of the planet and so forth? And that's of course much more difficult. And the next one is, of course, the chemistry. I would not even dare saying life. I mean, that is a very chancy kind of a thing, because as you well know, communication is slow. Even in the closest exoplanets, you have to wait for many years before you get an answer to your call.
Yeah. Professor, it has been incredible to share this webinar with you. But then we have come to the end. We thank you. And
thank you.
Thank the audience for joining us in this journey of 40 years. So thank you very much, and I hope to see you again at some point.
Okay. Goodbye. Thank you.
Thank you.
Bye.
Bye.
Thank you. Bye.